Yeah, welcome everybody to today's talk on the within the Design++ speaker series provided to you by the Design++ initiative of ETH Zürich. My name is Michael Kraus, and I'm happy to be your host tonight or this evening. It's my special pleasure to also welcome our guest and lecturer of today, Ms. Cynthia Brosque. I hope I pronounced it right or correct me. But before I introduce you to our speaker and her talk, let me shortly provide some background information on our YouTube channel, which you can find the link here. And you can also find there the information with respect to the talks and the speakers and the content. So the Design Speakers Plus series is a recurring event, usually taking place on Tuesday, Wednesdays, or Thursdays between 4 and 6, depends a bit on the speaker's availability. And in addition, we are very happy to share the launch of our brand new homepage of the Design++ initiative, which you can find here. You will find updates on our contents there, but also on the speaker series, the topics and the dates. And I want also to drive your attention that you can now subscribe to our calendar, so you can automatically have the Zoom links and the descriptions of the talks if you import that calendar. A bit more to the background. At the moment, there is a number of professors from architecture, civil engineering, and computer sciences of ETH involved in the Design++ initiative. For the running business, there is 3 leading postdocs responsible, which you can see here. And meanwhile, we have a larger teams of scientists associated to us, and I would refer you to our homepage to check on their bios and their fields of research. So in the case you're interested in the future of connecting AI, ML, or XR in the AEC industry, just reach out to one of us. We are more than happy to discuss any ideas or projects. I want to take that opportunity here to also again say that and announce that Romana just received a big grant for one of her proposals, which makes me personally very happy, and I think the whole Design++ team. And we will have, I think, a homepage added soon on background of that. So with this good news on the Design++, I want to give some more details on our speaker who joined us today. It is Cynthia Brosque from the Stanford University, and she will talk to us about the comparative analysis of robotic and traditional construction methods. Cynthia is currently a Ph.D. student and candidate in civil and environmental engineering at Stanford. She is conducting research under the supervision of Professor Martin Fischer, which I think most of you will know. Her research interests are virtual design and construction robotics. She holds a Master of Science in Civil Engineering from Stanford University and an architecture degree of the Universidad ORT in Uruguay. Please forgive my non-Spanish pronunciation. I put here the link to her homepage. So if you're interested in her publications and her research, I would refer you to that. So yeah, with no further words from my side, as I said before, it's a pleasure to have you here, Cynthia. And I would say the stage is yours.
All right, so hi everyone. So my name is Cynthia. I work with Professor Fischer. And today I want to share a little bit of our research in construction robotics. And specifically, I'm going to touch on how we can evaluate robots compared to traditional methods. So we've all been familiar with this. Manufacturing has radically improved the way that we can make cars thanks to the use of robots. It used to take us over 12 hours and a half to just assemble one car manually, with only a few cars produced each day. But today, cars are much more complex, even with way more parts, with 30,000 assembly parts. But we can send a complete truck down the production line in 53 seconds. However, when we look at construction, even in the last 100 years, productivity has remained mostly flat. I'm not going to put up the same chart, but you've seen this time and time again. And that is because, of course, we still rely on a lot of manual labor that is repetitive and also heavy for the workers. In some cases, like this one from Goldbeck, which is one of our industry partners, there's a lot of prefabrication off-site. And this has been able to improve the quality and the safety by working in a structured facility. But even in these cases, there are still some tasks that are strenuous and repetitive that need to be performed on site. So again, even if we are able to prefabricate and bring automation in that sense, there's still a need to assemble elements on site. But in the last decade, we see that new construction robots started to surge that were aimed specifically to perform tasks on the field. On the top, we can see Shimizu's drywall placing robot, and then Spot from Boston Dynamics, which I'm sure you're all familiar with. And then on the bottom right, you can see Enlink's concrete drilling robot, which now it's similar, it's kind of a previous version to the new HLT JBot. And so we've seen how influential robots have been in manufacturing, but of course it hasn't been so simple for construction just to emulate what happened in manufacturing. So our researchers, we started to notice all of these new construction robots that started to be tested and applied on construction sites. We wanted to understand where's the technology now, what's the readiness of these robots for the construction industry, where are we headed, and whether we'll have a similar impact in construction as we saw in manufacturing, why or why not. So I was actually very fortunate to learn from the first use of this concrete drilling robot in Norway. I was just kind of starting my master's in 2017, and this was sort of my first assignment to work on this case study. This was a robot produced by Enlink, and it was used as a subcontractor on one of Smith sites in Norway. And for me, what really struck me from this example was, okay, the technology seems to be ready because it's an actual robot that was able to operate on the field just as any other subcontractor. It performed work of good quality, and it even saw like really outstanding results in terms of the schedule savings and productivity. So it made me really wonder, why are we not using this more, and really sparked my interest into construction robotics. So today I want to talk a little bit of the points of departure from our research. So a little bit about how we can evaluate these new construction robots. Then I'll go down into the details of this drilling robot case study. And then finally, I'll talk about our conclusions and next steps, and sort of where has the research gone from that first case study. So starting from kind of the point of departure, as you all know, construction robots are not really new. We actually analyzed 114 papers from ISARC and ASCE from the last 3 decades. And we found a big spike on research interest in this topic in the 90s. A lot of the research was meant to analyze what types we can robotize, how we can bring more automation into construction, and also documenting the different advances that were happening around the world, especially in Japan. But when you read some of these papers, it seems like, you know, construction robots are imminent. And a lot of the authors even question what's going to be the impact on the workforce once these robots become widespread. But the truth is that that scenario did not happen, at least not at that moment. Maybe the technology was not quite ready then. And so we see kind of after that spike, there's kind of a slowdown in the research throughout the 2000s, early 2000s. But in recent years, again, thanks to the use of artificial intelligence, better and faster computing methods, and also the use of building information models in a more generalized way, has allowed us to see robots in more unstructured environments, and they are becoming more and more feasible solutions. Especially, we've seen a multitude of new new single task robots that have emerged. So as we saw kind of that outlook, we were interested in seeing, okay, so how can we, looking at what the literature has done, evaluate today's construction robots? And so we noticed, of course, that one approach has been to compare the traditional method, so the manual workers performing the task versus the robots. And of these case studies, like the overall research, 16 were kind of case studies done in this way, comparing the traditional work to the robot work. But we have noticed that a lot of these cases were tested in laboratories or still under kind of controlled environments off-site, which, okay, it still gave us a lot of really good information of how the robots could be deployed. But when we take these comparisons to the field, of course, we get a lot of new information and, of course, new challenges. The construction site, given that it is a very unstructured environment, still presents major challenges, even with today's technologies. And so we wanted to find out, okay, in these cases, what were the types of variables and how the authors proceeded with their analysis and their comparative analysis. So again, I highlighted here which ones were the field tests, because in this case, we really had a drilling robot which was used as a subcontractor. So it was deployed on site. So we were curious whether there were differences when robots were evaluated on a university setting or a laboratory versus on the field. And then we noticed kind of two types of variables that were usually addressed. And we classify them between dependent variables and independent variables. So what we mean by dependent variables are sort of the typical variables you can think of when we are evaluating a construction method. So we focus on productivity, cost, quality, and safety. And we try to map of these cases which ones were looking at these kind of typical construction variables. But then we also found in some of the cases there were independent variables. And in this case, we kind of classify them between product, organization, and process. So these were the variables in which an innovator could influence. So if you were the manager from a construction perspective, you can think of, in which project to deploy the robot. And that has to do, with some physical aspects of the construction site. So we classified that as the product. But you can also think about which organizations to involve, which have to do, of course, with the organization. And the process of how to involve each organization and when and what each organization has to do, which is, of course, part of the process decisions. We realize, like, first of all, these things are stuff that we can influence. So we can decide, for example, to use a very detailed building information model. And that is going to have an impact on also afterwards the quality of the product, perhaps. So these independent variables could have impact on the kind of dependent variables. And we also realized that there wasn't just one consistent way to analyze robots throughout the literature. So different authors maybe focus on a few of these variables, but not all. So it was interesting to notice that if we want to really kind of have a consistent method to evaluate robots for construction, we needed to kind of dive deep and see what has been studied in the past. So with that literature review, so we had this kind of independent and dependent variables that we knew we wanted to assess for the drilling case study. We kind of embarked in our comparison for robotic and manual drilling for installation hangars in the Norwegian project. So we started, as I mentioned, working on this at the end of 2017. The concrete drilling robot was used kind of for the first time as a subcontractor in one of Cruise Smith projects in Norway. Its goal was to release the workers from a very repetitive and strenuous task of overhead concrete drilling. And so we saw that kind of to give you the big picture, and then I'll go down into how we got to each of these results. So compared to manual drilling, the robot was able to cut 98% of the strenuous work hours in the drilling tasks. And it also reduced 12 hours of cleaning time because it had an integrated vacuum design into the end effector. It improved accuracy from 10 millimeters to 3.3 millimeters and rework from an estimated 5% to 3%. I do have to admit here, and I'll mention it throughout the talk, that in some cases the robot data was really easily accessible. So the 3% of rework was recorded. The robot tracked every hole that was drilled and holes that could not be drilled and the reasons. But for manual work, we had to rely sometimes on interviews and estimation from the workers that would say, okay, yeah, we usually consider a 5% rework, but it wasn't tracked in the same way. Also, the robot achieved a 1-week reduction across 4 project zones of 750 square meters, and it had some slightly increased costs by about 13%. And despite this kind of extra cost, the general contractor thought the robot was better than the traditional method, especially thanks to the health and safety contributions. And they advised that they apply the robot in future projects. So that's kind of the big picture. So when we go into sort of like studying what is this project, so again, because it was the first time that the general contractor used a robot, it gave us a very special opportunity to study what were the challenges and also the lessons learned by the company. And in particular, and this was kind of a coincidence, that 4 of the project zones were drilled manually and 4 were drilled robotically. And this actually gave us a really good basis for the comparisons because we had the same kind of robotic and manual drilling in the same environment with the same installation crews for ventilation, piping, sprinklers, and the ceiling. And so we started kind of building up the case study as soon as the project had just finished. And trying to go back, we talked to the general contractor, and they were really interested in trying to quantify what were the benefits, because they had kind of the, this thinking that, okay, the robot was really great and it had this time savings, etc. But they really wanted to have a method to quantify what were the actual results. And so we kind of started taking a look back and interviewing a lot of people involved in the process. And we also had surveys from the 16 workers that installed right after the robot worked, and who also worked in the other 4 zones. So looking at kind of this like product analysis, we're talking about single task interior robot, only designed for concrete drilling. We can talk about a little bit more about the hardware if you're interested about that. It had this kind of mobile truck and lifting platform, and it was kind of depending on one operator that moved the robot around with a tablet and a joystick. But once the robot was set in position within its workstation, it could autonomously drill all reachable holes. It required, power, and given its weight and sort of dimensions, you also needed an elevator on site to be able to transport it to the right location. And the optimal reach was between 2 meters and 3.5 approximately. And so kind of these parameters, also when you look at the construction site, it was really feasible to deploy this robot on this case because you had really an open space commercial project. The heights were about right for the robot. And so most of the holes were reachable, and it was a flat ceiling. Going a little bit into the organization. So in this case, the robot operated as a subcontractor. So it collaborated with the other trades on site, ventilation, piping and sprinklers, electrical and ceiling. At first, the trades did saw the robot as a competitor. So it was kind of challenging from an organizational perspective to introduce the robot because obviously the robot reduced a part of the work scope. And so of the 16 surveyed workers, 44% stated that this kind of reduction of their usual scope was the kind of the worst aspect about the robot. However, 14 of the 16 workers found some benefits to using the robot, like early finish, less physical strain, and more accuracy. A paper from Taylor and Levitt from, I think it's 2005, pointed out that when we're talking about diffusing innovation in project-based industry like construction, actually the number of organizations that need to come together to use that innovation can be a barrier in itself. In this case, for the innovation to be successful in the project, we had to align several subcontractors. If you only use the robot for one sub, then you would kind of miss on the synergies of drilling everything in one robot pass for all the subs. So in this case, having so many participants, of course, made the coordination a little bit more difficult, but it was necessary for the robot to be successful. So the organizations went from 5 participants to 7 when we look at adding, of course, a robot and then a third-party modeler, because in this case, we needed to have certainty of the hangars, and so they had to be modeled in 3D, and that wasn't something the subs would normally do or had the capacity of doing, at least in this project. So they had to hire an external entity to do that modeling. So we can also highlight other aspects about the organization, and the literature suggests things like, what's the worker's experience? Is this something where a task where we have availability of workforce? In this case, there was enough availability of qualified workers, but it might be impactful in other tasks. Unions was something else that was brought up, but in this case, they mentioned it wasn't particularly important because there was a good safety net in Norway for workers. So they were not particularly worried, but could be something to have in mind for other tasks or even in other countries. And finally, as we mentioned, the team has to decide what these participants will do when and in what sequence, and this have to do with the process decisions. In some cases, robot could change the typical process, not only to complete the task, but also the process to get the right information to perform the task. And so in this case, for example, the robot had to drill for the 4 subcontractors simultaneously, and also used automated data acquisition versus manually marking and drilling each hole from 2D plans, subcontractor by subcontractor. So when we look at kind of the process map from the manual side, so the baseline scenario and then the robot, from the manual perspective, we can see that each subcontractor occupied a zone at a time, and they alternated the drilling with the placing of a section of pipe or duct or whatever it was before drilling the second hole. So they were kind of alternating the drilling and installation tasks. And this was true for all the subcontractors, except for the ceiling one, which, similar to the robot, was able to drill all the holes in the ceiling in advance and then place all the ceiling drops because it's a very modularized system, but it wasn't true for the other subs. And on the other hand, when we go to the robot, we see first a lot of tasks that have to do with getting the right information, doing extra clash detection to make sure that the holes are in the right position. And then the work was organized within workstations. So each workstation was an area in which the robot could drill autonomously without needing to boot computers and doing kind of a new setup. So in this project, given like the zone's geometries, we had 2 workstations per zone. So you can see here kind of the task is divided by the setup task, and then the robot drilling, and the operator would do the color coding right after the robot drill, but he could have his coffee and enjoy some time while the robot do the hard work on the drilling. And so the same for the other side of the zone. And finally, some kind of quality check at the end to make sure that everything was okay. And also I wanted to highlight that sort of this color coding was considered to be a really good and transparent method to keep track of the progress of the different subs on the field. The sort of detailed information that was needed about the task. So as you can see here, it's a really detailed building information model at level 400. And so we needed information about the X and Y coordinates, the depth of each hole, diameter, and also the trade to be able to color code it afterwards. And so this certainty in the beam coordination, even though of course it took some time, it actually brought 2 other key benefits. So it resolved 50 clashes in the Solibri model checker that would have otherwise appeared on site. And Chris Smith estimated it would take about 10 hours to solve them on the field. And also the workers mentioned that spatial conflicts were reduced in the zones drilled robotically. It also allowed with the LOD at 400 to prefabricate hangars because we also had the detail designed. And so all of these things that came from having a very detailed building information model, of course, manual work could have also benefited from that, but only robotic work was planned with this approach. So we also wanted to highlight the benefits of having this building information model in a very detailed way. And so these implications on the product organization and process decisions, of course, we can now analyze them in terms of the safety, quality, schedule, and cost, which are our main dependent variables. So I'll quickly go through these four. Of course, safety is one that is paramount, and in many cases, it's the motivation to deploy robots in construction. We usually want to distance the workers from this sort of very heavy, repetitive, and noisy work conditions. And we know, of course, overhead drilling is a task that is associated with really high rates of shoulder pain and muscular disorders. But when we really wanted to drill down and be able in the case study to determine, how many incidents are there in a project or what could be the impact on the insurance rates if we use a robot, it was actually very, very hard to come up with a number. So it's something that we are currently working on how we can better estimate this or associate some cost impact to the safety benefits of the robot, but so far it has been difficult. But what we could do was to try to analyze, what's the percent of heavy work hours over total work hours in the task. So look at it from an ergonomic perspective, and also the qualitative data from the work conditions that the workers discussed. The robot, of course, had the chance to distance the workers from the noise and be able to absorb the dust from the drilling hole. From quality perspective, of course, when we are talking about robots in construction, we expect them to have better or at least the same quality as the traditional methods. So we can study several variables like accuracy, repeatability, or rework. In this case, the question of how accurate the robot is was kind of difficult to answer. It wasn't as straightforward as I would imagine it to be. So the robot arm itself had a repeatability of 0.1 millimeters. So this means that if nothing else changed, so the setup didn't change, and you ask the robot to re-drill the same hole, it will 100% of the time hit the previously attempted hole. However, because of calibration of the total station and also the ceiling plane sensor, the robot company talked to the subcontractors and asked them, what's the acceptable maximum deviation that you have right now, because we want to make sure that we are respecting that tolerance. And so the manual workers estimated that 10 millimeters was an okay manual accuracy. So, all right, the robot tried to hit the 10 millimeters, but then when they actually measured it, they were a bit more accurate. So they had an overall accuracy of about 3.3 millimeters. And then finally, in terms of rework, the robot, as I mentioned, logged all the holes that could not be drilled. So for example, the causes for robot rework could be that the hole was too close to the slab edge, or maybe it was going to hit rebar, so it couldn't be completed, or there was some mistake in the coordinates that were given to the robot. But in manual work, of course, we don't know that granularity of the rework causes or the number of holes that had to be redone. Going from the schedule perspective, so the literature has typically compared productivity of the traditional crew to the robot by looking either at the number of holes per hour, so that kind of productivity analysis, or the cycle time to produce one unit, or in this case, to drill one hole. So of course, we wanted to start the analysis in that same way as the literature suggested. So we looked at kind of trying to break down the different subtasks to drill one hole manually and with the robot. And we can see that the robot was a little bit faster just in the drilling of one hole. However, in this scenario, we actually knew that the robot was able to, in the zones drilled robotically, to save about 1 week. And this is what was reported from the site. And so we kind of, but we didn't have a granularity on, a record of each task, how much time it took. So we did kind of a bottom up and top down approach to the traditional schedule. So from the top down approach, we had, that notion of, okay, the robot saved 1 week, and that's what we observed on site. But then from a bottom up, what we did was, from the very detailed process diagrams, we tried to ask, the managers and the workers, okay, how much time do you estimate like this particular task took? And so we tried to build up the schedule from scratch, and also using kind of the cycle time analysis from videos of the robot working and also the manual workers performing the task. And we knew, of course, the exact number of holes. So it did took us some like effort to produce the schedule, and it was something that we realized in future projects we need to document properly as the task is being done. But of course, in this case, we didn't have the chance because we started doing the analysis once the project finished. It was really good from the robot perspective because the robot task reports had exact information and on the production rates and the number of holes drilled each day. So it was definitely easier to do this kind of recap of the information from the robot perspective. And so when we look at, we started saying, okay, we started from 1 hole. Now what is the next scope possible? And we wanted to find out what would happen if we only use the robot to drill 1 zone. So given the number of holes of 1 zone and the work of the 4 subcontractors, we actually realized the robot would be not as efficient in this case because of the considerable coordination effort at the beginning. And this was because of this kind of extra clash coordination and getting the right information from each of the subs. And then when we go to the 4 zones, which is what actually happened on the field, we see here kind of this 11% reduction, so this 1 week reduction in the robot drilling versus manual drilling. And this is because kind of the initial effort of coordination would be similar for 1 zone as for the 4 zones, at least in this case, because all the zones follow the same rules as far as the installation go. So the robot company said that it actually, for them, once they do all this prep work and all this coordination, the best would be to drill as much as possible once they get to the site, because that's how you can get the most efficiency out of the robot. After doing this, of course, from here we can discuss what could be the best plan. So you can start thinking, okay, what could happen to the schedule if we also worked overnight, or if we had 2 robots instead of 1 working simultaneously. And so these are all things that we can try to envision where robots could actually have their best efficiency. But we tried to stick to kind of what happened in the field and trying to reconstruct what was the sequence here. And so finally, from a cost perspective, so traditionally, a lot of the literature focus on return on investment from robots, but today we're seeing a lot of different models. So robots used as a service, so in this case, as a subcontractor, and that can help reduce the risks, especially from the general contractor perspective. You don't need a big investment at the beginning of the project. You can just charge, this robot, I think, charge per square meters, but you can kind of agree on a service cost that makes sense for the project. So here you can see the way that we looked at the robot versus manual cost was, okay, we looked at drilling and installation cost from the manual perspective and then from the robot side. So that's why you see some labor hours even on the robot column. And then, of course, we had some kind of coordination and robot service costs, which included also the robot operator. And that gave us this kind of 13% increase in the cost, which was absorbed in equal parts by the 4 subcontractors, the owner, and the general contractor. So it was kind of a special situation because it was the first time that it was being deployed. And so that's why it was kind of divided in equal parts. I think in the future, it would also make sense to see how each individual sub is benefiting from the whole. So maybe instead of charging per square meters, you can think of ways of charging per hole and try to figure out which sub had most holes, for example, or other way of figuring it out. But in this case, they just divided equally. So some challenges on this analysis, of course, was, in a sense, the lack of traditional data. So we had to rely a lot on estimations and interviews, and also trying to define what's the right comparison boundary. We saw this could be challenging in different tasks. So in this case, we accounted from kind of the coordination process until the quality check process. But depending on how you decide your comparison boundary, you can also maybe see the benefits from a different lens. And then some challenges specifically from the application. So the second one, having to coordinate the information from the trades, was actually quite challenging. Afterwards, the company was also working in having Dynamo scripts to automate the rules placement. But we figured out when we use some of these robots, we also learn a lot from the traditional process, and sometimes even what we are lacking in knowledge from the traditional process. So this was a task that was typically resolved on the field with the workers' experience. But if we had to a priori kind of ask them, where would you put the holes? It wasn't like so clear where the holes needed to be for, optimal resistance and mechanical resistance of the materials. So it was interesting how I think the robot kind of uncovered also things that we need to improve. And then process changes to be able to have the certainty of the work scope. The drone contractor said that even if they don't use the robot, they will now still always require the level of detail from the building information model, because that helped them save a lot of the clashes and the issues that would arise on the field. And then, of course, the challenges that came from adding one new organization and reducing the scope of the workers, and how in the future we can kind of train also the current workers to be the robot operators, since they will require some basic knowledge about the robot, but then also it's setting up a total station. It's tasks that we could normally also assign to workers, and how we can train them to do these tasks. So just to kind of conclude and tell you about our next steps from this research. So after we finished this case study with Link and Chris Smith, we kind of wanted to see, okay, what are other robots that are being tested and deployed on site? And so we did two more very in-depth case studies, one with Bildar and Veidekke in Sweden, and the last one with Dusty Robotics and Mortenson, which it was really fun because we were able to take this layout robot to one of Mortenson's big sports center facilities here in the Bay Area. And we realized kind of our initial thesis was that if construction companies had a consistent way to evaluate robotics according to different priorities, then they could make more informed decisions about their feasibility, and that could reduce the effort of deploying construction robots. So from the insights of the literature review, we also looked at a little bit how manufacturing evaluates robots, and we incorporated that into our evaluation. And from also kind of the variables that were important in each of these cases, we developed a robotics evaluation framework. So on a kind of bigger sense, we first want to check if the robot is feasible, and looking at project and robot variables about the product, the organization, and the process. And this can, of course, be an iterative process, because we can start thinking, okay, we're going to deploy this robot for this project, but then realize that that is not the right one. So we want to make sure that we select a project that is feasible. And then we can sort of evaluate what could be the impacts in terms of safety, quality, schedule, and cost. And as we saw from some other evaluation methods, we want to have the possibility to weight priorities. So in one task, safety could be really important, but maybe in another one, if the cost is not right, then you wouldn't really use it. And so trying to align that to what are the client and the project objectives to deploy the robot, and to be able to make final recommendations. And so right now we're working on a class with 10 robot companies. And so
I would like to, is it recorded? Okay.
Oh.
So guys, sorry, I said please mute.
Oh, no worries. So yeah, now, and I'm actually really excited to share this. We have developed a new construction robotics class this year at Stanford. We have graduate students from civil engineering, and they are each of the group of 2 students is working with one of these construction robotics companies, and also with a general contractor. And they are we want to scale up this evaluation and have data from a lot of the robots that are being tested or deployed on site today. So we want to find out what detailed insights can we get from doing the same analysis across very different types of robots, what comparison variables are very difficult to evaluate and why, and what is the effort to make such comparison. So how many hours would it take you to figure out if one of these robots is right for your project? And what are challenges that they envision in choosing and using these construction robots? So that is basically where we are at today. If you want to find out a bit more information on the drilling case study, there's the link to the paper that was recently published. And if you have any other questions about the class or anything else on the research, I'm also happy to respond.
Yeah, thank you, Cynthia, again for this very nice talk and intense discussion. Yeah, your time and effort is really appreciated from our side. We were really happy to have you here today. And yeah, as I said before, I will upload the information to this talk and the recording also to our YouTube homepage in maybe someday. And eventually, I want to highlight our next talk, which you can see here in roughly 2 weeks, given by Tim Sandy, who was also at ETH here on the topic as well on robots. And yeah, we will see each other hopefully again on the 23rd of February, starting at 4 p.m. And yeah, thanks again. Stay safe and see you next time.